today we look at a topic, namely fin heat transfer or extended surface heat transfer, which has got a lot of applications, right. If you basically look at heat transfer, the study of heat transfer, essentially heat transfer is studied for three objectives, okay, as far as I can see. There could be only three possible objectives for studying heat transfer. The first is you study heat transfer with a view to increase the heat transfer in certain situations. A, that is to increase heat transfer. B, to decrease heat transfer, that you want to do some insulation design, and C could be temperature control, that is certain equipment will work only at certain temperature. So, the idea of studying heat transfer is to achieve one of the three objectives. You augment or increase heat transfer, you decrease heat transfer, and third will be to do temperature control. But if you want to do any of these three, first you must know what is the governing equation to the problem, solve it and prove that the correct solution is correct, and then start looking at parametric study, or the alternative route is to do experiments, measure the temperatures and find out whether it is under control, or build a prototype and find out whether you are able to augment the heat transfer, whether you make a 1:20 or 1:30 scale down reactor, find out whether the heat of the fission, it is possible for you for the sodium to carry away the heat. So, you will do scale down experiments, or you do experiments on water, and then from water you know the Prandtl number of water, you know the thermal conductivity of water, you know the Prandtl number of sodium, and this thing using your fundays of Reynolds number, Prandtl number, Preclet number, Nusselt number, you see whether you can map. So, if this is the heat transfer coefficient, if this is the heat transfer rate I am getting with water for the scale down reactor, what will be the heat transfer I will get for the full reactor with sodium, something like that you have to do, right. So, in the context of these three objectives, now if you want to increase heat transfer, basically we are talking about increasing convective heat transfer. So, the governing equation is basically the rate equation, the Newton's law of cooling, Q is equal to now if you look at electronic equipment, the number of transistors per unit centimeter square is keeping on increasing. So, when the number of transistors is increasing, I squared R losses keep on increasing. Therefore, the amount of heat which you have to dissipate keeps on increasing, but at the same time the size of the equipment also is continuously decreasing, right. People want to pack more and more with in less and less volume. Therefore, there is considerable challenge in cooling these electronic devices. Therefore, there is no choice but to augment the heat transfer. So, now if you want to augment the heat transfer, there are three ways of doing this. So, Q will go up if H goes up, correct. From this equation, this is to indicate increases. So, Q increases when H increases, but what is the difficulty in doing this? First of all, H cannot be indefinitely increased. H increases means the pumping power will also increase, okay. Now, Q increases when delta T increases. Are you getting the point from here? So, can you allow the computer to work at 200 degrees centigrade? Not possible. In many of the situations the delta T is fixed, delta T is not fixed, the T max is fixed, the T infinity may be changing with seasons during daytime, night time, but delta T little bit you can play. It is not, you are not completely free to change it, more or less fixed. So, therefore, most of the times the only option is to Q increases when A increases. That means you are augmenting the heat transfer by increasing the heat transfer area. So, you use extended surfaces. Right. So, the goal is to increase the heat transfer rate. However, if you use the extended surfaces, the H may marginally go down, because if you put some fin and if make air flow over it, the flow path may become little more complicated, therefore, the H may go down slightly, but H into A with fin will be much higher compared to H into A without fin. So, the delta T remains fixed, the Q with fin has to be will in general be greater than Q without fin. If this Q with fin is less than Q without fin, there is no point in adding fins. Therefore, you do not add a plastic fin or a cork fin or a bakelite fin. What is the use? You will add a fin with a material of high thermal conductivity, so that there is no additional conduction resistance which is generated. You put some additional surface and it generates conduction resistance. What is the use? Okay. So let us look at one such extended surface or fin. This is pulled out of a desktop computer. We just did it 5 minutes back. So this is the fan. Okay. The fan is to increase the H little bit to whatever limit is possible. So this is this dedicated fan. This fan and the heat sink sit on the processor. There is one more fan which is on the back side of the tower, okay, which is the general fan which is cooling all the parts. This is dedicated for the CPU because CPU is critical. CPU is the heart of the machine. Okay. Now if you see this, what sort of fins are these? Material, aluminum. Aluminum has got a terrific thermal conductivity 205 watts per meter per Kelvin. What process do you think they would have used to do this? What manufacturing process? They are extruded components. Okay, they are all extruded components. Now this is a constant area. All the fins are of constant cross sectional area. Yes, they are rectangular fins. This is a typical heat sink. Okay, so those people will not do detailed calculations at what we are going to do today. These people will say so many meters, so many watts per so many meter square. How many meter square are required for every watt, and then they will use a thumb rule and do it. But now when things become smaller and smaller it becomes more tricky. For example, in the laptop we will use a heat pipe, and then back side the whole surface loses heat. The whole back side of the laptop is actually the fin that is losing HA delta T to outside. When it is hot outside, there is a convective heat transfer taking place by natural convection. That is the eventual heat sink. That is where the heat is transferred outside. So this is a simple example. So examples of, so this is a fin, so a fin system. So vertical fins standing on a horizontal base. So there are so many examples of such fins. When you roadside, when you see transformers, the transformer, there is an oil which is going inside. So to cool that oil, you have transformers. You have fins. You have got fins on the electrical motors, electrical generators. You have seen. So fins are there everywhere. Now we look at the heat transfer aspects of analysis of a fin. So basically, so you can see that examples. Heat exchanger tubes. So you can have like this. Okay, or you can have like this. Right? You can have this bottle and you can have fins like this. Which type of fin you will use and all that depends on, you have to do an analysis, wow, how much heat transfer augmentation you want to do and what is the weight you can afford, extra weight you can afford and so on. Alright. Now, and so on, there are so many things. You can also use, these fins can also be used in outer space, okay, in a spacecraft. If there is electronic equipment in the spacecraft which is generating heat and you have to maintain it at a temperature, then you can still use heat sink, but the heat dissipation will not be by convection to the outside, it will be by radiation. The normal heat sink, both modes of heat transfer are available, convection and radiation. Now let us take a simple fin. So I am drawing something like this, okay. I am taking one fin, right. I am taking one fin, and For as far as this fin is concerned, this length of the depth of the fin is much larger compared to the length of the fin, and then the thickness is very small, therefore temperature is a function only along the length of the fin. I do not worry about temperature in the vertical direction or temperature in the z direction. So it is a one dimensional steady state problem where there is no heat generation, okay. There is no heat generation within the fin, there is heat generation outside, but it gets on to the base, that heat is dissipated, okay. So I can say that this is T, length is L, right. Now the heat transfer coefficient is H and T infinity. The heat transfer coefficient can be because of natural convection or forced convection. In this case the heat sink, it will be because of forced convection, okay. So the base temperature so that is the design variable. For the CPU you may want to restrict to 60 or 65 degrees. Some electronic equipment 75, 80 you can go, above 80 the reliability of the equipment goes down, okay. So T base, assuming that it is known, T infinity is known, H is known. Now so the width of the fin is W in the direction perpendicular to the plane of the board. Assumptions. T is a function of x only, K is a constant, QV equal to 0, okay. H and T infinity are constant, okay. K is a constant is alright, QV is a constant is alright, H is a constant, T infinity is a constant, T is a function of x only. These three assumptions are questionable. T is a function of x only, H is a constant, T infinity is a constant, these are questionable assumptions, but let them remain questionable assumptions, but if we complicate it we cannot analyze it further. But you should know that when you solve an actual problem you may consider these to be variable and use advanced methods for solving. For today's class we will keep them as constant, then we will proceed with the analysis. Now we will have to take elemental now let us take an elemental slice which has got a length of delta x. So Qx is the heat which is entering here, this is Qx plus delta x, okay, and from both sides I have Q convection. Okay, if you take any fin here from bottom side and bottom and top there will be heat transfer. Now if you consider radiation we are in trouble, you have to consider view factors and all that, let us omit radiation for the time being, okay. It becomes more complicated if you want to, right. Now using energy balance, no, we are not solving for an unsteady fin, okay. Steady state conditions exist using energy balance. Whatever is entering must be equal to whatever is leaving, okay. Therefore Any problem? What happened? So let P be the perimeter of the fin. Now dqx is that correct? The elemental area of that slice is P delta x. Watch out, A is the cross sectional area, W into T. The Fourier's law is always for the cross sectional area, right? Newton's law of cooling is always for the surface area. Okay. So did we say that K is a constant? Yes. A is a constant? A is a constant, may not be constant, but for our consideration we have taken a rectangle fin of a constant cross sectional area. But suppose I have a fin like this, or I have a fin like this, then I am in trouble, but that will lead to Bessel function. Okay, that will lead to Bessel function, modified Bessel function, first kind, second kind, k naught, I naught, k1, but I used to teach all this before, but now it is not required. You can do it on the computer itself, right. Let us not worry about the variable area, constant area, therefore we are looking only at constant area. So let us say we can adjust the minus. Yeah, sure it is there. Okay. Now let what is theta? Yeah, temperature excess. Okay, therefore equation number 6 is known as the fin equation. It is an ordinary differential equation, it is a second order equation, it supports two boundary conditions. The two boundary conditions are pretty clear to us. At x equal to 0, the temperature at the base is known. At x equal to L, that is at the tip of the fin, several conditions are possible. You can have a convection condition, you can have a radiation condition, you can have a convection plus radiation condition, or you can have a very simple condition that you ignore the heat transfer at the tip and say that the fin tip is adiabatic or insulated. Okay. But now this Hp by Ka is called the fin parameter, the square of the fin parameter. because the heat transfer coefficient, perimeter, thermal conductivity and area of cross section of the fin, all of these are available before we start the analysis. Therefore, you can calculate HP by Ka and take the root of that, that will be m, the fin parameter, that gives you the horoscope of the fin, fin with low m, fin with medium m, fin with high m, that will give you an idea of what will be the efficiency of, ultimately the efficiency of the fin. Now I am using one more term, efficiency of the fin, I will define it at an appropriate time. Now we can, so this is Kelvin per meter square, this Kelvin per meter square, this Kelvin, therefore m square will have 1 by meter square, m will have the units of, okay. It looks like a silly thing, but this m is the fin parameter, this is the meter, okay. So okay. Now boundary conditions, did I write the d square theta by? Will be equation number 9. So the fin equation given by equation number 7 along with the two boundary conditions 8 and 9 close the problem mathematically. It is now possible for us to write the general solution to the problem and apply the two boundary conditions and find out the solution, right. Let us do it now. So the general solution to 7 is given by okay. So where you can write the solution as a e to the power of mx plus b e to the power of minus mx, but for strategic reasons I want to keep the cos h. You can start the solution with a e to the power of mx plus b e to the power of minus mx and then you can work out, but the algebra is more involved for this boundary condition. Alright, now the challenge is to come out with the constants a and b and then find out k d theta by dx at x equal to 0, find out the heat transfer from the base, then what will be the maximum possible heat transfer from the fin. Therefore actual heat transfer from the fin divided by the maximum possible heat transfer gives you the efficiency. Then what is a heat transfer with fin divided by what is heat transfer without fin, that is called effectiveness. Once you have all these numbers, then for an actual fin for the heat sink which we pulled out of the desktop computer, we can actually find out what will be the fin. I can straight away say that it will have some 98% efficiency, you can't do any more. It is already aluminum which is having a terrific thermal conductivity, it is so thin, and then this will be more or less isothermal. So the key point is if the fin is more or less isothermal, you are going to get good efficiency. The challenge is to make it isothermal, do not make it 1 kilometer long. If you make it 1 kilometer long, the tip of the fin will be at the temperature as outside. Therefore the last portions of the fin will be very poor in transferring the heat. So it is always advantageous to have more number of short fins rather than small number of long fins. Okay. So that will become clear once we get the temperature distribution, how the temperature distribution looks like. Okay. So theta a cos h mx plus, okay, but your common sense tells you that the common sense tells you that temperature should go like this, right. Cos h mx in fact is a good candidate for this because it is a composite of e to the power of mx plus e to the power of minus mx. Okay. Now x equal to 0, is that correct? Sin h of 0 is 0, cos h of 0 is 1. All right. Therefore, now you have to apply the second boundary condition. Is that correct? D by dx of cos h will be e to the power of mx minus e to the power of m will be there. Okay, so it will be m sin h mx. This will be m e to the power of mx plus m e to the power of minus mx divided by 2, m you take out, it will be sin h will be m cos h mx. Because there is a minus sign, you will be tempted to believe that it will be minus cos h mx, it is not. Okay, it is cos h mx. Okay. Now therefore, yeah, why a theta b, therefore minus km, all right, minus km now where am I applying this? At x equal to 12. What is that? Is it fine? Collect the terms with b. That's km, h theta b, is it? Do you have h theta b?
No sir.
No.
Just h.
Km theta b? No.
No.
Km cos h, very good, equals, both are minus now, right? Plus h, yeah, tell me if I made any mistake, is it all right? theta b is should be fine. Therefore, B is no theta B now we have to be careful. This is the boundary condition at the tip. Watch here. The boundary condition at the tip minus k d theta by dx is h theta at x equal to L. There is no need that the h for the fin which came in the fin parameter root of hp by ka should be the same as this. So I will make it, I will be more cautious and call this as h tip, correct. Because the tip heat transfer coefficient could be different, because it may be a combined convection radiation, or because this is basically along this it is heat transfer from a horizontal surface, but at the tip it is heat transfer from a vertical surface. There could be small differences. Okay, the tip is a vertical surface, isn't it? So the heat transfer from a tip is applicable. How you calculate a convective heat transfer from a surface which is vertical? This will become very critical if it is only natural convection. A surface placed like this and a surface placed like this will give rise to different heat transfer coefficient. My famous example of this, Limca bottle if placed in the fridge like this or this, which will give maximum heat transfer coefficient, which will give maximum cooling? Why? Because of the growth of the boundary layer. If the boundary layer develops like this, the boundary layer grows only up to this height. So the average boundary layer thickness will be much smaller when it is placed like this. If it is placed like this, the boundary layer will develop like this. So the average boundary layer thickness will be more. Boundary layer thickness is a resistance to the flow of heat. Thicker the boundary layer, lower the heat transfer rate. Therefore, the average boundary layer thickness for a vertically placed Limca bottle is more than the average boundary layer thickness in a horizontally placed Limca bottle. Therefore, all these fellows, bakery fellows will put that is also for compacting. They want the porosity to be less. That is one more thing. But this will cool better. Like that? No, because Deepak didn't like when I say horizontal is different. Now you understand? When you are blowing air and all that, if it is forced convection, it won't matter much. But still, vertical plate, horizontal plate, different correlations are available. Okay. So in order to be clinically correct, we will have this. Now, 16. B is obtained. Therefore, Abhinandan, what is the problem? Did I miss anything? Therefore, is it correct? Thank God, theta b is on both the terms, so I can bring theta b to the left hand side. Okay, I can bring theta b to the left hand side. Therefore, Okay. So let us cross multiply. I can take the huh? Oh, of course, without that I am in trouble. Now any objection? Is it fine? I removed the Km from both the numerator and denominator. Okay. Now I can cross multiply. Basically you have to collect the terms with h tip by k and the terms without that. What is cos h a cos h b minus sin h a sin h b? Cos h of a minus b, correct? Cos h a cos h b minus sin h a sin, you can do it, you can do e to the power of mx and check it out. Therefore and cos h mx sin h ml minus cos h ml sin h mx is sin h of m into L minus x. This material must be new to you. No undergraduate textbook on heat transfer has given this. They will always consider the case of an adiabatic fin tip and then they will use a correction and all that, right, because it's not really complicated, we can derive it. Most US books prefer not to do this, they will take the simple adiabatic fin case and it's fine. Sin HML cos HML, that is what you get. Now what is the heat transfer from the fin? Minus Ka d theta by dx at x equal to 0. Please remember, whatever heat is coming from the base, this is only convected out. This is what we wrote mathematically as d squared theta by dx squared is minus m squared theta equal to 0. That is a formal mathematical statement of the energy balance. Therefore, if you find out what is the heat transfer which is entering the base, that is the heat which is convected out. Alternatively, I can find out what is the theta at every station x and then I can divide the whole fin into several stations and find out HA delta T for each of these sections and numerically add up. that will also be the same. What Pullarao, you did not follow? But this is analytical formula is available, we will do this, okay. Both should be equal with the numerical limits, okay. Now, so this Q fin must be equal to minus Ka theta b. Now this will be cos h ml minus x plus h minus m plus m. This minus is there, so this will be m and because there is a minus L minus x, there will be a minus which comes again. Now this you have to substitute at x equal to 0. Is that correct? What is the answer you are getting? Is it very complicated? No. So Q fin Kam theta b sin HML
plus h tip by mk
plus
cos HML plus h tip by k.
Okay. So as the algebra gets tougher and it is almost about to consume you, I will give you some relief. For most practical cases, we can assume that the tip is adiabatic. We can substitute h tip equal to 0, okay, for the adiabatic fin. Does not mean it will be absolute 0 in relation to the h, from the other surfaces it is negligible, you do not have to consider. Okay, what will this become? Therefore yeah, you have to give some numbers, is that okay? Agreed?
If you substitute that only you get this.
Okay. What is the Q maximum? What is the Q maximum from the fin? When will the maximum heat transfer take place from the fin? If the fin is isothermal and is at a temperature equal to T base theta b. Therefore, the surface area corresponding to that will be perimeter into length. So, if you use the Newton's law of cooling HA delta T, H into P into L into theta b, that is a maximum, that is the denominator. Numerator is Q actual from the fin. If you divide Q fin by the Q max, it will give you a performance metric or like a CGPA of the fin, whether the fin is working all right. Maximum value is 1, minimum value is 0. Let us do that. Q max equal to, when whole fin no okay, therefore the fin efficiency divided by is it okay? The efficiency of an fin with an adiabatic fin tip is tan HML by ML. Okay. Now, there is something called the effectiveness. So, this, look at this, now you got surface area, that is front side, top side, bottom side of each of these fins, okay, and so many fins are there. If you find out the efficiency and the total heat transfer from each fin, you can get the heat transfer from all the fins. Now, if the fins are not there, this base surface will be there, that base surface will transfer a heat equal to HA delta T. Now, you have to find out what is the heat transfer from the fin divided by heat transfer without the fin, and if it is not greater than 2 or something, do not add fins, do not add a plastic fin and screw up the heat transfer. Okay. So, this is the effectiveness. So, this is a performance metric. Now, this should be greater than 1, it is not an efficiency parameter. Now, this will be equal to denominator. Denominator, please tell me the denominator.
It's assuming same
thickness into the
H into A. What is the A? WT, correct, into no number of fin, only one fin for every fin, theta B. So, this is without, okay, this will be K also, A also goes. So, Km tan HML divided by yeah, K is watts per meter per Kelvin, this will be per meter, so watts per meter square per Kelvin divided by this. So, this must be greater than 2 or else do not use fins. You can quickly see that What is tan h of 2? No, tan h ml, tan h of 2 0.96, tan h of 3 0.98 or 99. Therefore, tan h ml is not a big parameter once m crosses certain value. Therefore, if the fin has to be effective, please look here, the fin has to be made of a material whose thermal conductivity is high. The fin should necessarily be having a material which has a reasonable value of m, okay, but length should not be very large. It should have, and there should be low heat transfer coefficient for you to justify. If there is a surface already with a high heat transfer coefficient, you are very energetic, you put lot of fins with a poor thermal conductivity, you are botching up the whole thing. You should know where to put the fins. The fin should always be put on a surface on which the heat transfer coefficient is lower. If there is a tube, water is flowing inside, air is flowing outside, you do not do an optimization and put a fin on the inside. Already terrific heat transfer coefficient is available. Okay, you should know where to put your money, as I say, so the fin should be on the outside. The fin should always be on that side where the heat transfer coefficient is weak, because that is the controlling resistance for the overall heat transfer coefficient. Okay.